Alright, time for another draftphysics.com, debatephysics.com. Also, but you can't debate people who aren't here. Yeah, it is people who don't even know the argument exists because, frankly, people wish to hide it and run away from it and evade it and all of that crap. And it's quite disturbing how people are okay with that. An internet run by little certain groups of people, like the little editors at Wikipedia or the workers at the Googleplex, and they're going to control what's on the internet and what human beings are allowed to talk about. And it doesn't really bother anybody. It's just pretty pitiful. But it's just an example of everything else that's pitiful about human civilization and how it fails so dismally because humans fail dismally to have any integrity or honor. Yeah, they just don't have any of these qualities. It'd be nice if they had some of them, but they just don't. All right, unfortunately, people suck. It's just a fact. Anyway. All right, so as usual, I will give you the truth about what an electric current is, and then we'll read the silly Wikipedia page. It doesn't have anything to do with the subject, pretty much. I mean, they're just so clueless regarding how the thing actually works. And what their obligation is instructors, okay, in explaining something. So the simple concept is you have a conductor, and we have two things that we can do here. We can send single things with a very high velocity or pressure, or we can send multiple things, okay, lots of them, with a low pressure each, okay. And so one is the voltage, the pressure is the voltage, okay, and the number ends up being the amperage. And so you can just really, it is an equivalency to momentum. What's really going through the wire is force, and that is synonymous, as Newton would say, with momentum. All right, what you're basically saying is the mass is essentially the amperage. All right, and the pressure, the voltage, all right, is the other component that'll tell you how much watts is going to go through the wire. All right, and the other feature is, so amperage is this. Amperage is volume, okay? It's the amount of electrons, and the amount of electrons will decide essentially how many atoms are going to be affected in the wire, because the amount says that all the atoms have to get involved, where if there's a small amount at a high pressure, just like a lightning bolt, it doesn't only go, the lightning bolt doesn't go through the whole atmosphere, it just goes through the part it needs to. So there's no volume problem for a lightning bolt in terms of getting the pressure from point A to point B. And it's only a problem if the discharge happened through a huge amount of volume of atoms. But the other fact is, like I said, is the important aspect. So first, it's a volume. Okay, amperage is a volume of electrons number. And second is that it's key, this volume thing. The affecting atoms is what makes magnetism. So the magnetic component of what a current, an electrical discharge can create is entirely dependent on how many atoms it moves. It has to move the atoms in the conductor, all of them, not just this lightning bolt thing. It has to have so many electrons coming in that all the atoms are getting pushed. And so all the atoms are getting polarized. And if you polarize, the more atoms you can polarize, that is, the higher the amperage, then the higher the magnetic effect. And so they should make that clear that amps cause magnetism. Magnetism isn't caused by voltage. It isn't just caused by momentum in a way. It's essential that there be a volume of electrons, and you affect a lot of the atoms. So you have to have a high amperage. You have to have a high amperage and a low voltage, all right, to maximize your magnetic effect. Now you could have a high voltage, but the problem with a high voltage at a high amperage is you've got way too much momentum going through your wire and it's going to melt. So if you lower the voltage and increase the amperage, you'll get more magnetism. You increase the voltage and lower the amperage, you get less and less and less. So it's just about the number of atoms affected. So volume affects more atoms, voltage affects fewer atoms, and you're really just transferring force, okay, which equals momentum through the wire. Okay. But this page won't say anything about those two facts, the essential facts. And so we'll read the garbage the Wikipedia editors say is the physics of electricity. They insist you must believe. And if you disagree with them, they will ban you. Okay, you're not allowed to even say it. They won't allow themselves to be publicly challenged to respond to the assertion that they are not accurately describing the mechanism. All right, so this isn't the main article. This is the electricity article, but anyway, it's probably going to be fairly parallel, called electric current. So the movement of electric charge is known as electric current. I mean, its a voltage is essential, so I just don't think that's what they should call it, but whatever, let's play. All right, the intensity of which is usually measured in amperes. I don't know what else it's measured in, so whatever. Current can consist of any moving charged particles. So anytime you're moving electrons, but you really can't move protons. It is just kind of nonsense. Most commonly, these are electrons. So he says most commonly, but shouldn't it really say essentially, okay, except in very high specialized experiments, you're not going to be moving protons. But any charge in motion constitutes a current. I'd say that's sort of ridiculous, but whatever. Electric current can flow through some things, electrical conductors, but will not flow through an electrical insulator. So we know that the insulator and the conductor, the difference is that the pressure isn't shared in an insulator. So the atoms inside the material can't share their electron pressure. Their pressure is fixed, and they can't modify it. And so a conductor allows you to modify the pressure of the atom's electrons. So all the atoms are connected to each other, and all of the electrons have a separation. And if you disturb the separation in one portion, you disturb the separation in the entire conductor. And that's the real distinction between a conductor and an insulator, is the capacity to share electron pressure. So an insulator can hold a charge, but it can't share the charge. Can't move it. By historical convention, a positive current is defined as having the same direction of flow as any positive charge it contains. So, well, it's just kind of silly, right? Positive current. There's no such thing as a negative current. So what's the, it's a silly statement. Are to flow from the most positive part of a circuit to the most negative part. So again, it's just, we know it's a flow of electrons. You're either increasing or decreasing something's charge potential, the pressure of the electrons, and that's it. And their direction of flow is always from high pressure to low pressure. It can't flow the other way. All right, current. Yeah, high pressure to low pressure, right? You can't, yeah. Current defined in this matter is called conventional current versus unconventional current. It's just such nonsense. The motion of negatively charged electrons around an electric circuit, one of the most familiar forms of current, is thus deemed positive in the opposite direction to the electrons. So instead of just saying, look, we misassigned the whole thing, so we'd have this wrong notion that the electrons are somehow, okay, the thing you're adding and subtracting, well, no, it's the negative component that you're adding and subtracting. And it just by convention, it would just been better if they would have assigned the idea of north-south or plus minus oppositely, because the assignment's just unproductive. Because the point is you're increasing electron pressure, not proton pressure. Okay. So current and voltage have to travel in the same direction. They have a notion that current travels the opposite direction, but it's just a mathematical notion. It doesn't have anything to do with reality. And it's just kind of, like I said, I mean, this is a tragedy of science. Now, this isn't something they should be describing this as one of the mistakes of science, is that, they can't get their verbiage right and understand that this is simply an increase and decrease in the number of electrons and the pressure between the electrons, and that's all we're talking about. That's all electricity is. However, depending on conditions, an electric current can consist of a flow of charged particles in either direction. So again, it's only electrons, and you're either adding or subtracting pressure. So again, just nonsense. Or even in both directions at once. So, who could be bothered with this? It don't happen. Okay. The positive to negative convention is widely used to simplify this situation. The positive to negative convention is widely used to simplify this situation. So it doesn't have anything to do with the truth or accurately understanding what the process is. And the process is the speed of light process. So I thought of that about gravity. So I guess I'll throw this in. It's just a little... Let's say that gravity is hitting you. This is a little discrete particles, and they come down and they hit you. Like a conductor, you're going to do kind of the same thing. It's all going to be hitting one spot, up here mostly. It comes in through the sides. But, you could think that the force would end up being collected by the electrons on the outside first, or substantially. And that they have to convey the pressure to the rest of your body. But that would be the easy thing to sort of understand, is that pressure is going to be pretty easy to convey because it's going to happen at the speed of light. So you're not going to notice that maybe your head does get compressed more than your feet, because it's happening at the speed of electricity, essentially. The electrons are communicating the pressure. All right, in some respects. Now, obviously, individual cells have a distance between each other, and they actually have to, push on each other to affect a change in pressure, and that sort of gets to the subject of insulators. So obviously, we're not entirely electrically connected, but you can understand that if I did put you in an electric circuit and I put electricity at one end of you, it will travel to the other end of you, okay? It will travel through you. And you could argue that in much the same way as electricity would move through you, that gravity could also move through you. Okay. It will change your electrical potential. If the electrons are more squished on the top of your head, you end up having an electrical potential, a voltage, and your body's going to neutralize it. Kind of an unnecessary bit, but I'll throw it in. It's all for free. All right. The process by which electric current passes through a material is termed electrical conduction. Yeah, well, let's just see what it said. And so electrical conduction is electrical resistivity, is a fundamental specific property of a material that measures the electrical resistance, or how strongly it resists electrical current. So we're not saying it never resists. It either is capable of sharing electron pressure, or it isn't capable of sharing electron pressure. So it doesn't have anything called resistance. It has either the electrons can communicate with each other easily in terms of their pressure between atoms, or they can't. A low resisted indicates a material that readily allows electrical current. So again, and what is an electrical current? It is a transfer of a potential in terms of the pressure under which an electron is under. Resistivity is commonly represented, so it's just bullshit. So that was disappointing. and its nature varies with that of the charged particles that the material through which they are traveling. So the charged particles, you say that doesn't say anything. They could say some atoms share electron pressure better than others. All right. Examples of electric currents include metallic conduction, where electrons flow through the conductor, such as a metal. So we know that all of it is electrons flowing, okay, and it just matters on how connected the atoms are to each other. That's it. So if there's a smooth path between the electrons, then the electricity flows easily. If there's not a good path, in the sense that there's a lot of breaks between the atoms or different things, and the electrons have to actually, whole atoms have to move or something, then it's going to be a very slow and retarded process of moving the pressure. And I think that's electrolysis, but anyway, where ions, charged atoms, flow through the liquid. So you have a whole atom that's carrying the potential. So you send it in packets, of atoms that are missing or have too many electrons, and so you just send the electron pressure by a vehicle of atoms themselves. So you have passengers in a car. So the electrons take a car trip, instead of just flying there. All right. Let's see. Flow through the liquid or through plasma, such as electrical sparks. Well, that's sort of a tricky word there, isn't it? So they're just using the atmospheric atoms, okay, and creating a path of ions. All right. While the particles themselves can move quite slowly, so we know, no, they don't. They move quite quickly. The electrons aren't ever moving slowly. All right. And it just means how fast are they. The higher the voltage, the higher the speed, but even the low voltage is a pretty high speed electron pressure. It moves between the electrons very quickly. It's always at the speed of light between the electrons. So if these were both electrons, the idea is the pressure that they're pushing on each other is always at the speed of light. So this pressure, no matter how fast this moves, their communication is always at the speed of light. So this could move slowly, and this will move slowly, but they communicated it very quickly. So this slow part isn't much of the movement, right? The little jitters of the electrons is a small percentage of the distance. These electrons are, relative to their size, you could say, they're hundreds of miles apart, and they're only going to move a few feet. So this one moves a few feet. 100 miles away, this one moves a few feet. But they communicate that 100 miles at the speed of light. So the communication of the pressure is always very fast. All right. So again, they have it just wrong again. And they're going to say the words drift velocity, and it's just absolute garbage junk physics. While the particles themselves can move quite slowly, they can't move quite slowly, and it's just about how much distance they actually move. Okay, so you could argue that the higher voltage means it just moves more distance. All right, sometimes with an average drift velocity only fractions of a millimeter per second. So we know that drift velocity is nothing. So we'll read it, but it's nothing. In physics, drift velocity is the average velocity. So this is, again, they're telling you you're moving cars by, let's just say, banging into cars that are right next to each other in a parking lot. So you hit one car and the other cars move. They're arguing that because 4 cars moved, we're going to take the speed of those 4 cars and dilute it by dividing it by the total number of cars in the parking lot. You didn't move. You only moved 4 cars out of 400 in a parking lot. And now they're going to take that velocity of, say, 10 miles an hour and divide it by 400. You didn't move all the other cars. There's no such thing as a drift velocity. There was the 10 miles an hour, not the 0.04 miles an hour that you turned it into by saying all of the atoms, all of the electrons in the wire moved. No, they didn't. It's just wrong and stupid. And yet here it is. They're telling us this is in 2004. The best science can do is to talk about something that's complete nonsense. It doesn't have anything to do with the function of the wire and how it works. All right, only fractions of a millimeter per second. So again, just nonsense. The electric field that drives them itself propagates at close to the speed of light. So the electric field, okay, there's not an electric field, there's just the momentum of the electrons. So you're moving the momentum. That's it. You're transferring momentum like a Newton's cradle. You're just transferring the momentum. That's it. Nothing else is happening. All right, enabling electrical signals to pass readily along wires. So it's not about sending signals. It's about the fact that you're sending an actual physical force is traveling through the wire. All right, and it's traveling through the wire by electrons pushing the force into each other. Current causes several observable effects, which historically were the means of recognizing its presence. Okay, well that's interesting. There's so many ways it doesn't. You can't see the current. And you only see it when there's too much of it, usually. Okay. That water could be decomposed by a current with a voltaic pile was discovered by Nicholson and Castile or something in 1800, the process known as electrolysis. All right, so you could put the electricity in, create a bunch of ions, okay, and you would end up breaking the water molecule into its hydrogen and oxygen because it was aggressive enough to split the water molecules into hydrogen and oxygen. Their work was greatly expanded upon by Michael Faraday in 1833. Current through a resistance caused localized heating. All right, so anything, it's pretty hard, okay, except for like a superconductor, which takes all the heating out, I guess. It's one way of looking at it. It makes all heat disappear quickly, so it can't cause any trouble. It gets it out of the wire very quickly. So let's just think about what's the best way to say it. The fact is the more impure, the more insulating atoms are inside the material, you could argue. The more atoms there are that do not communicate their electron pressure with the other atoms, just disturbs the process and creates these places where you end up with a bottleneck and the pressure gets higher or lower and then the direction of the force gets turned. So if the force hits a pressure wall, then it's going to tend to, like ocean water, it's going to tend to try to find some other direction. And when you start changing the direction of the current, that's when you're going to start losing the force. The force is going to be leaving in directions you don't intend it to. All right, their work was greatly, okay, Faraday. Current through a resistance causes localized heating, an effect James Prescott Joule studied mathematically in 1840. Now, that's a funny term just because Joule basically did a ton of physical experiments. He didn't do mathematical abstractions. One of the most important discoveries related to current was made accidentally by Hans Christian Ørsted in 1820. So again, we're told about Ørsted, who doesn't get much credit, and then there's apparently other guys 100 years earlier in 1720 who had already discovered it anyway. When, while preparing a lecture, he witnessed the current in a wire disturbing the needle of a magnetic compass. He had discovered electromagnetism, a fundamental interaction between electricity and magnetics. So the point is that when you change the pressure, when you're moving an electron from one atom to another atom, you're changing the polarization of the atom. There's a period in there where the protons in the nucleus are now visible because you're taking an electron that is in this position and you're moving it to this position. So you can see that the proton force would now not be blocked by the electron. So moving the electron means you're changing where the proton force can be seen. So in a sense, the signal being sent from the object, if you thought of the protons in the nucleus being red and the electrons being blue, you can understand that the signal, red, blue, is changing. And that's magnetism. All right. A fundamental interaction between electricity and magnetics. A level of electromagnetic emission generated, the level, by electric arcing is high enough to produce electromagnetic interference. So this is, another way of they should be saying is what it's doing is releasing, the force, the photons, the force moving the speed of light is leaking out of the conductor. So the little picture here of an arc is basically showing you this is the force now not going through but leaking out, flying out. You've broken the wire's insulation down, and now you're seeing the stuff, the hose is leaking, so to speak. All right, which can be detrimental to workings of adjacent equipment. So the point is it's not only creating visible light, that is all the colors, but it's a white light. It's also creating microwaves and radio waves and gamma rays and X-rays. So it's creating a whole bunch of frequencies, not just visible light. And so yes, you can interfere with a whole range of radio signals because you're creating a transmitter by creating the arc of electricity, because it's got contained in it all kinds of frequencies. Should I try to explain that? Yeah, probably not here. But that really, I guess, just has to do with the different atoms. And the fact is that each one can emit an electron at a different velocity. And when the electrons are moving at different velocities, that's creating a different signal. So if I move my hand this way, I'm creating one kind of frequency. If I'm moving this way, and then I go slow, and then I go fast, and I go slow. And that's what's happening, is that when the force is being released, it's not being released at a consistent pressure because it's being released by electrons that aren't necessarily leaving the surface. They're just vibrating on the surface. And they're vibrating at different speeds depending on where they are in the atom. So the ones deep in the atom vibrate quickly. The ones on the outside of the atom vibrate slowly. And you're vibrating all of them when you cause this effect of having too much current and too little conductor. All right. In engineering or household applications, current is often described as being either direct current or alternating current. So that's just a naming convention. And so it, whether it should be called wattage or, because it's not just about current, it's about the voltage. So you're really talking about a wattage in a wire. It's not just a current. These terms refer to how the current varies in time. So, it's alternating momentum, direct momentum, alternating force, direct force, or alternating wattage and direct wattage. Anyway, direct current, as produced by example from batteries, and required by most electronic devices, is unidirectional flow. Is a unidirectional flow from positive part of the circuit to the negative. Why would you call it unidirectional? You don't think of unidirectional as being one directional. So I guess that's not how I would say it. I'd say it's one directional flow. All right. If, as is most common, this flow is carried by electrons, as is always the case, frankly, they will be traveling in the opposite direction. Oh, so why did they say that again? Anyway, it's just, they're not traveling in the opposite direction. Anyway, alternating current is a is any current that reverses direction repeatedly. So this is a tricky question because you're really not talking about having to alternate the current. You're talking about stopping and starting the current. So an alternating current can also be one that just goes from on to off. It doesn't have to go from reversing a direction. So you can create, you can use a transformer with a current that isn't changing directions. As long as it's turning on and off, it'll work. All right. So where was I? Alternating current is any current that reverses direction repeatedly. So all it has to do is stop and start. But regardless, almost always this takes the form of a sine wave, or it takes the form of a on, off, on, off, on, off. All right, anyway. Alternating current thus pulses back and forth within a conductor without the change moving any net distance over time. So again, you can move a net distance over time by pulsing, okay, a DC or a one-directional current. The time average value of an alternating current is 0. So again, who cares? You know it's momentum, so you know if you're being shooken to death, you know a real thing has happened. To say, well, the net motion is 0. No, it isn't. Okay, the net momentum is 0. Well, no, it isn't. But it delivers energy in first one direction and then the reverse. So again, it's applying, it's exchanging force by moving a lever back and forth. And you can understand, you move the lever back and forth, you're still doing work in one direction. If you just create a cog or some other mechanism that you just keep pushing it in one direction and it doesn't push in the opposite direction, so you can create unidirectional motion out of alternating motion. All right. Let's see. Alternating current is affected by electrical properties that are not observed under steady state direct current. Okay. Alternating current is affected by electrical properties that are not observed under steady state direct current. So it's not about what you observe, it's about what's actually happening. So a direct current creates a signature that doesn't change. So once everything is changed, that is, once you start doing this exchanging stuff, it becomes a consistent pattern. That is, you end up with how to say it? You end up with a view that's all pointed. The change is permanent. So once you put the electricity in, you make a change to the view, that change stays. All right. Now, if it was alternating, then it's going like all the way in, all the way out. The gates are closed, the gates are open. Let's see how to explain that. Let's see. So the direct current, I'm trying to think of an analogy for the fact that it's just stabilized by the one direction. And if you were to reverse the direction, then everything would flip. And then everything, it's like the blinds opening, blinds closed. Once they're closed, they have an appearance and it stays that way. And if they flip open and close, then you can see the change. Something like that. All right. Such as inductance and capacitance. So for some things to react, you just can't send a signal if it's always closed, right? You can't send a signal unless you have something to send the signal, two conditions to switch. So there's no inductance because once you've charged something, all the change is already taken place and there's no more change happening. These properties, however, can become important when circuitry is subjected to transients, such as when first energized. So that's hardly a transient. But yeah, that's the whole point. Is that when you're first doing the change, closing the blind, it's closing. So you're always going from a even if you're going to reverse voltages, you're always just going from a low number of electrons to a high number of electrons. It doesn't really matter where the ground is, where you're saying positive and negative is. So you're just changing the pressure in the wire, and every time you change the pressure in the wire, you change the position of the electrons, and you change what the external world sees. The wire looks different. So if you pump DC in, the wire stays looking one way. And if you pump alternating current in, then you can see the different states that the wire is in. All right, electric field. Okay, I guess that's worth doing. But it's just the wrong kind of, again, it's, you know, it's not an electric field, okay? It's the actual source of the momentum. I mean, it's the actual force is the field. The force between the electrons, the electron force. So in a sense, the electric field is just the electron force, and you're just changing the potential, the pressure of that force. How much force there is between the electrons. Again, that's the key component. You're just changing the pressure between the electrons. You're pushing them closer together, or you're pulling them further apart. All right, so the electric field always exists. So there's no creating an electric field. The field of energy always exists. The charges are always reflecting the universe in a way in which whatever goes in, it comes out blue out of electrons, it comes out red out of protons. So they're just excreting the energy that comes in, purple. This makes it red, this makes it all blue. That's all that's happening. And all you're saying is that I can change the appearance of that field, okay, by having more electrons blocking this. All right, or less electrons blocking this. And so it's just about how these things are oriented, how they're next to each other or arranged with each other, that changes the electric field, that changes the field that everything sees. Everything is seeing all the time, and all you're doing is changing the pattern they see. So there is no electric or magnetic field. There's just the field of charge force. There's just the field of force, and all you can do is change whether it looks bluer or redder. And that's it. You change this pattern. Red, blue, red, blue, red, blue, or it could be blue, blue, red, 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 blue, blue, blue. The pattern decides how something else, what it's going to see. So, you know, you could make an exaggeration out of it, and it's the difference between it seeing a duck or an elephant. Seeing a, you know, lion attacking or a butterfly. The rest of the world is sensitive, okay, to those patterns. The certain things are sensitive to the pattern. They can see the pattern because they're getting hit a certain way, and they react. So that's like the magnetic materials. All right. But there's always a field, and all you're doing is changing the pattern in the field. So that would be the key concept. I'm saying their shit is shit because they think some new field is being created, that they're creating energy. And they're not creating any energy. They're just making something more effective in affecting something else where it was ineffective before. So it's a tipping point argument. It's a seeing argument. It makes the field more visible to something else. So you could argue that the photons, they're all the same, but you can't see the radio waves, and you can't see this. You can only see certain ones because they affect it in a certain particular way. It's the same energy hitting you. It's just that one form of energy causes a chain reaction of absorption, where you can move your electrons, and another form won't move your electrons. But it's the same energy. It's just in a different arrangement. And in one arrangement, it affects you. In another arrangement, it doesn't. All right. probably some other way to say that. You could sort of understand it in waves in a swimming pool or something. If they have a resonance to them, you can, move, and if they're chaotic, you can't. It's things like that. The concept of electric field was introduced by Michael Faraday. So the problem with Faraday is that he didn't make a clear distinction between lines of force and what he called field lines. And field lines are an abstraction defining where there's equal potentials. That is, there's purple. Okay, you can draw lines where it's purple, and then you can draw lines where it's red and blue. And it's the red and blue lines that are the important ones, not the purple lines. An electric field is created by a charged body in a space that surrounds it. All right, so it doesn't create the field, it just changes the pattern in the field and results in a force. So there's no new force, there's just a change in the pattern of the force. Okay, exerted on any other charge placed within the field. An electric field acts between two charges in a similar manner to the way that gravitational fields act between two masses. So that's really, they should have made a clear distinction that's only true between opposite charges. And like it extends towards infinity and shows an inverse square relationship with distance. So it's just the basic argument that it would appear that electrons and protons are spherical. They don't have an up, down, side, or any of that crap. They do the same thing as a point radiating. However, there is an important difference. The difference was you should have just made the point that like charges attract like gravity, and like charges repel, and only opposite particles attract like gravity. Gravity always acts in attraction, drawing two masses together, while electric field. So there is no electric field, while a change in the field can result in either attraction or repulsion. So if I'm an electron and I'm blue and I'm affected by blue, then if the field turns blue, I'm going to be pushed away. If the field turns red, which I can't see, right? So I've changed the frequency, I've changed the form, and now I can't see it, and so now it goes right through me. I'm transparent to it. I can't absorb it. All right. So one I can absorb, the other one I can't absorb. So obviously I'm going to be pushed away. Now, even though it's the same force, it has the same potential momentum. I can only be moved by one form of it. Since large bodies such as plants generally carry no net charge, the electric field at a distance is usually zero. Well, that's to say that there's no electric field when there's a magnetic field, I would say is just kind of playing again semantics. Thus, gravity is the dominant force at a distance in the universe, despite being much weaker. So again, it's not much weaker, it's that it's a nuclear force. Gravity is affecting electrons and protons, and the electrons and protons motion is not minuscule, in a sense that obviously when you add it all up, it becomes a rather significant force. So when you move electrons and protons, you create gravity by consuming force moving matter. All right. An electric field generally varies in space, and its strength at any one point is defined as the force per unit charge that would be felt by a stationary negligible charge if placed at that point. So you're just saying I'll use a blue thing or a red thing to measure how much blue or red there is in the field. So that's all you're really saying. How red is it? How blue is it? And purple is like half, of course. So, but that's all. You're just using the test charge to measure what the pattern looks like at this particular point. The conceptual charge termed a test charge must be vanishingly small to prevent its own electric field disturbing the main field. And obviously, its field isn't going to be able to affect anything because it's going to be so small. All right, so in most cases, if you're measuring a magnetic field with a few electrons, those few electrons aren't going to disturb your big giant magnet. And must also be stationary to prevent the effect of magnetic fields. So it's not going to do any of that. It has to interact. So there's no point in not allowing it to interact. So I don't even understand. The whole point is you're testing the field, and you have to test it by hitting the electron or the proton with the field. As the electric field is defined in terms of force, and force is a vector. So again, this whole idea that even having to say that force is a vector is ridiculous. All momentum is a vector. All motion in the universe is a vector. There's no motion in the universe without a vector, having both magnitude and direction. So nothing moves in the universe without magnitude and direction. It never happens. There's no such thing as motion without magnitude and direction, without velocity. Okay. It follows that an electric field is a vector field. So I don't know why they did this exact diagram, because what you're really doing is testing the charge. Okay, it has a consistent lines, right? Can you see that silly illustration? Yeah, mostly. And the point is this is it's admitting all red force, and it is only pushed by red force. So it's going to measure how much red force there is. But again, these field lines, these are equal potentials. These are just telling you where there's an equal amount of red and blue. So they've put this test charge next to a surface that is negative. And what they should be, they could have showed you is a test charge next to something positive. And the field lines will be different. But the point is the lines of force are just, they're emanating in straight lines off this surface, and they're hitting the red thing with straight line paths. There are no curved lines for the lines of force, and the lines of force are doing the actual moving. All right. Let's see. An electric field generally varies in space, and its strength at any one point is defined as the first. Okay, we did that. Sorry. The study of electric fields created by stationary charges is called electrostatics. So that's just charge. The field may be visualized by a set of imaginary lines whose direction at any one point is the same as that of the field. So they're just saying which way will it move in this complex field. Like the field's not just a direct line between red and blue. It's more complicated than that, and so they end up with these lines that aren't, again, they're not the real lines of force. The electron would actually move. Let's see how do I say this. Obviously, it's if it's changing how local, what it's reacting to, and it's moving, it already has a momentum. Then you can see why it would move a curved path, like creating an orbit. And the other, so every time it moves, it's changing its position, it's changing the amount of force that's affecting it. And so having lines for where the charge moves is interesting, but it's not the force that caused those lines, it's the charge. All right. Point the same that this concept was introduced by Faraday, whose term lines of force. So that's the term where that Faraday ruined, because he wasn't talking about lines of force. He was talking about field lines. So what Maxwell makes clear is a distinction between lines of force, those are what he draws off of a charge, the straight lines coming out of the charge, versus the field lines, which are the abstraction about drawing where there's an equal amount of blue and red. Still, sometimes see use. The field lines are the path that the point positive charge would seek to make, so against the path the particle takes, rather than the stones being thrown at it that's causing the path. The gravity causes, right? Gravity causes something to move. Well, the thing moving, the gravity, is a straight line force. It doesn't do curves. So it's the pressure that's changing, and that's changing the direction. But it's because you're combining two momentums. If you didn't have two momentums, it would all be straight lines. As it was forced to move within the field, so it was forced to move within the field. They are, however, an imaginary concept. Well, that's the only part that makes sense, is the lines the lines of force are real. The field lines are imaginary, with no physical existence, and the field permeates all the intervening space between the lines. So you can draw it as 10 lines or 100 lines or 1,000,000 lines, but that's the idea. It's like the sun. I could draw it with a bunch of little rays coming out of the sun. I could draw 10 rays, or I could buy 1,000,000 rays or 1,000,000,000 rays. And maybe when I get to a gazillion, I might have something close to the truth. But, but you're just saying that you're going to give it a proportional amount of pressure it's producing. But the fact is, the rays coming off the sun are straight line rays. Those are the field, those are the lines of force. All right. But how they affect something, how they push on something, and how it travels is just arbitrary, based on what you're moving and what that moving thing had as its own momentum. Field lines emanating from stationary charges have several key properties. First, they originate at positive charges and terminate at negative charges, and that crap doesn't happen. So they're saying we have to believe, okay, that somehow the force comes out of one thing and it goes into the other thing. That doesn't happen. Second, they must enter any good conductor at right angles. Huh? Yeah, what the hell did he just say there? They originate positive charges and terminate negative charges. Second, they must enter any good conductor at right angles. What the hell could that mean? Don't know. And third, they never cross nor close in on themselves. So the point is there's all there are is the electrons, and then there's energy hitting it constantly, and the energy reflects or is transmitted through it and changed. And those are the only two options, really: reflection or absorption. You move it, either you change its motion, it reflects, or it goes in, it comes out a different color, and is inert. But those simple, that's all it's doing. So all of that is straight lines. There's no non-straight line being emanated from a charge. It's all perpendicular from the surface. Yeah. Nothing reflects at an angle. It either reflects straight back, or it's absorbed as a straight, but there's no force ever angle in, angle out kind of thing. None of that ever happens. A hollow conducting body carries all of its charge on its outer surface. The electrons are seeking to lower their pressure. All right, high pressure always goes to low pressure. And where's the place you can go to create less pressure? Well, if it's hollow, you can understand going in here wouldn't be a great idea, because there's nowhere there's no way to escape the pressure in here. So obviously you go out here. So the pressure goes to the outside, not to the inside, just like the pressure on the earth is pushing out, not pushing in. All right. The field is therefore zero at places inside the body. So I would argue that obviously the field is not zero. It's that it's balanced. It's equalized. So there's plenty of gravity. If I made a hollow sphere, there's plenty of gravity in the sphere. It's just that it's always equidistant proportional. That is, there's always the same amount pulling you this way as pulling you that way. So there's plenty of force. It's just equalized. So the big difference between saying there's no force inside and saying there's an imbalance inside. There's no imbalance in the force inside, but there's plenty of force. Just like there's plenty of gravity in that space between the moon and the earth where you could go and you'll be weightless. Well, there's plenty of force acting on you. The moon's pulling you one way and the earth's pulling you the other way. So there's plenty of force acting on you. But from your perspective, it doesn't motivate you to move. So that's all you're measuring it by. Is, does it motivate me to move? No. But it doesn't mean that both objects aren't tugging on you. Both are tugging. Both pulling. So they really shouldn't say it's zero force. Okay, it just has zero potential, okay, to move you, but it doesn't have, there's not zero force. This is the operating principle of the Faraday cage, a conducting material shell which isolates the interior from the outside electrical effects. So it just allows you to be in a neutral condition of having no potential. A non-changing potential. All right. The principles of electrostatics are important when designing items of high voltage equipment. There is a finite limit to the electrical field strength that may be withstood by any medium. So this is more of an amperage argument, frankly. Beyond this point, electrical breakdown occurs and the electrical arc causes flashover between the charged parts. So again, this is just air. This is a problem of atmosphere. So there isn't any discharge in space. For example, air, for example, tends to arc across small gaps in electric field strength which exceed 30 kilovolts per centimeter. So, a centimeter of distance at 30 kilovolts and the atmosphere, the pressure, will cause the atoms in the atmosphere to create a conductor that the electrons can use. Over larger gaps, the breakdown strength is weaker, perhaps 1 kilovolt per centimeter, and there's always some kind of leakage. Like I said, little tiny, the atoms are flying off as ions. So you're creating lots of ions from the surface. Every atom that bounces into the surface will pick up an electron, for example, and take it away. So slowly but surely you're going to lose all of the charge just to the fact that there's a bunch of atmospheric atoms touching the surface and taking the charge away. The most visible natural occurrence of this is lightning, caused when charge becomes separated in the clouds by rising columns of air and raises the electrical field in the air to greater than it can withstand. So again, it's not the electrical field in the air, so that's just wrong. There's the fact that there's a condition that will move the atoms, and the atoms will start to consolidate in an area because of that pressure, and then eventually there's enough of those atoms for the electricity to travel through them. The voltage of a large lightning cloud may be as high as 100 million volts and have discharge energies as high as 250 kilowatt hours. So 250,000 watts. Seems like it'd be more than that. Anyway, the field strength is greatly affected by nearby conducting objects. It is particularly intense when it is forced to curve around sharply pointed objects. All right, so this is another point where, you can do a whole bunch of physics just about why charge accumulates on pointy things. This principle is exploited in the lightning conductor, the sharp spike which acts, a lightning rod is what they're talking about, which acts to encourage the lightning to strike, to develop there rather than to the building it serves to protect. So that was the problem, though. Is the fact is the lightning rod has to be well insulated from the building, or you're just going to collect the lightning and cause it to through induction blow up whatever's in the building. Anyway, apparently they had that problem with the first lightning rods, because they thought they were going to use up the electricity, but what they were doing is forcing it to be more local. I mean, they were changing where there would be lightning, and you sort of want to change where there would be lightning to as far away from the building, not where the building is. I guess I would argue you don't want to collect the lightning where the building is. You want to collect it where the building isn't. But anyway. All right. So I think that we'll leave it there. And then we can do... So electrical potential would be the voltage argument. We'll see what kind of mess they make out of that for the next one, I guess. And we'll move to magnetism. And then we'll say we've covered most of the important subjects and such. So anyway, my argument is Wikipedia says you have to believe this. This is the only possible truth. They are correct. This will stand the test of time. Nobody could argue with any of the crap stated in this retarded article because they're the gods of physics and they know best. And no, it can be demonstrated logically that it's nonsense, and it really isn't appreciating the real function. It's not describing it, and it's not acknowledging it, and it's just an insult to human intelligence that these weasels won't allow the argument to even take place.